All right, so now we're looking at some more types of differential equations. These are called homogeneous differential equations. So take a look at some examples here. The first ones, those can be solved by separating the variables. So we did that already from group 3 the other day. So we already know how to do that. The next set, though, can't separate them. Yes, we have both independent and dependent variables, but really difficult to separate them. So what are we going to do in this case? So maybe we can make a substitution of some kind. If we take a look at these in more detail, notice that can we show them, because they're in terms of x and y, can we show the right-hand side as a function of y over x? So for example, let's take the first example. Let's solve for dy dx. So that's going to be basically here, we're going to bring this term to the right. So that's going to be negative bracket x squared plus, minus y squared. And then divide by 3xy. Factor in the negative 1, so that's really y squared minus x squared over 3xy. And then we can split that up into, here we can look at dividing top and bottom by, well, multiplying by 1 over x squared. So that's what you're often going to have to do. So if we do that, actually I'll do it on the next one here. So here, 1 over x squared. I'm trying to get y over x. So if I can get rid of this x in the denominator and put it over x, that would be 1 over x squared. So let's look at that. That's going to be y squared over x squared minus 1 over 3y over x. All right, so then that's the same as y over x squared minus 1 over 3 times y over x. Okay, so then you can basically, the function that you're starting with is x squared minus 1 over 3x, and you're replacing with y over x. Next one, this, using your log laws, that's x over y. So if we want it in terms of y over x, it's just going to be negative log. Here we can split this up into 2 terms. That's going to be 1 minus y over x. Okay, so really not much, we don't really need that, brackets around that. Okay, so all of those we could express as a function of y over x. So that's what you call a homogeneous differential equation. So in this context, homogeneous means the same degree. So a function in x and y is homogeneous if all of its terms are the same degree. Sometimes a differential equation is written as mxy, so some function m in terms of x and y, dx plus n xy dy equals 0. So an example is that first one. Okay, notice how degree of m and degree of n are both 2. Another version of the definition of homogeneous differential equation is an equation of that form. Okay, m and n are homogeneous functions of the same degree. So that's the biggest thing. So here m is x squared minus y squared, so degree 2. And this is 3xy, degree 2. So all terms have the same degree. Right? How do we solve these? Okay, so in order to separate the variables, a substitution of z equals y over x, or rearranging that, y equals zx, will be used. This means that dy dx will also be changed. So if we have y equals zx, then to get y dy with respect to x, derivative of y with respect to x, we have to use the product rule. So that's going to be z times 1, derivative with respect to 1, plus x times dz dx. And that's what we're going to use. Okay, if we solve for y, then that's going to be, dy, then it's going to be z dx plus x dz. Okay, so we're going to use that to help us. So, first example. dy dx equals x minus y over x. So let's use your substitution. So first of all, we know from before, dy dx is z plus x dz dx. Okay, and we know that y equals zx. Okay, and so left side here is going to be z plus x dz dx equals, then, well, here we could actually show that as 1 minus y over x. So remember z, you can show this either way, z equals y over x. So that's going to be 1 minus z. Now, let's solve, let's collect like terms. So we're going to get x dz dx equals 1 minus 2z. Now it's in terms of two variables, right? And so we can separate. So here that would be 1 over 1 minus 2z dz equals 1 over x dx. Now we'll integrate. So that's going to be ln of 1 minus 2z. And so when we take the derivative, so remember we can substitute u equals 1 minus 2z. So du equals negative 2z dz. Okay, and so, not minus 2 dz, so that's going to be negative 1/2. I'm going to get rid of the negative 1/2. We're going to multiply both sides by negative 2. Okay, now it's in terms of z. So I want to substitute back in. So remember, z is y over x. So this is going to be ln of 1 minus 2y over x. And then I can bring the terms together. So the log terms together. When I bring that over to the right, that's going to be really x squared. The argument. Now I'm adding logs, so that's going to be ln of x squared, 1 minus 2y over x. So actually I'm going to multiply that in. So that's going to be x squared minus 2xy. So absolute of x squared minus 2xy equals e to the negative 2c. And then that means that x squared minus 2xy equals plus or minus e to the negative 2c. I'll bring that to the right. So then that's going to be x squared plus or minus e to the negative 2c equals 2xy. So y equals x squared minus e to the negative 2c over 2x. Okay, and then if you want to show this as a constant, where the constant is any real number, then you would have x squared plus, oops, that shouldn't be c there. That should be 2x. Okay, and then you could also show that as what? X over 2 plus k over x. No, what did I just do? Yeah, x over 2 plus k over 2x, which again, you could show 2x. So you could change that to a constant as well. Okay. Next one, differential equation. So we can't split that up. And now we know it actually passes through a point. So we can find our c value. All right, so remember, we'll let z equal y over x, or y equals xz. And so then dy dx, remember, is going to be z plus x dz dx. And then we'll replace. So y is xz, x plus xz. Okay, and then notice here, if we multiply through by 1 over x, we get z over 1 plus z. And so now let's get the z's together. Common denominator. So that's going to be z minus z is 0, negative z squared. Okay, now we can separate them. So it's going to be 1 plus z over z squared, negative out front, dz equals 1 over x dx. You can you can just split this up into two terms. So that's actually going to be negative 1 over z minus negative 1 over z squared minus 1 over z. Integral on that. Okay, so negative 2 plus 1 is negative 1. So that's going to be positive 1 over z minus ln of z equals ln of x plus c. Okay, now your point is 1, 1, but we're in terms of x and z here. So so z is equal to y over x, so it would be equal to 1. Okay, so z is equal to 1, x is equal to 1, y is equal to 1. So 1 over 1 minus ln of 1 equals ln of 1 plus c. Well, ln of 1 is 0. So c equals 1. So now our equation, we can now put that back in and start also substituting back in expressions for z. So remember, z is y over x. So this would be 1 over y over x minus ln of y over x equals ln of x plus 1. Let's bring the lns together. This is going to be x over y. I'm going to subtract 1 equals ln of x plus ln of y over x. And so when we multiply those together, we get ln of y. Okay, so let's get a common denominator here. Actually, let's do that in this step. So that's going to be x minus y over y. So then absolute value of y will equal e to the x minus y over y. So y will equal plus or minus e to the x minus y over y. Now we're at the point 1, 1. So our y value is positive, so we're just going to take the positive. Okay, so if you put 1 in for x and 1 in for y, you get 0 here, e to the 0 is 1, so it works. Okay, so back to the first example that we talked about. So let's get dy dx together. So dy dx, we did that, and we showed it on the first page of the notes like this. Okay, so then remember, let z equal y over x. So that means y equals zx. And when we take the derivative dy dx, in terms of z, we get z plus x dz dx. If you forget that, just differentiate that. So now y is zx. Okay, and so we can divide by, well, let's simplify this. So z squared x squared minus x squared over 3zx squared. So x squareds go into all of it. You can multiply, or you can show it as 1 over x squared. Okay, and then we have z plus x dz dx. So now let's collect z's. Bring the z term over. And that, with a denominator of 3z, is going to be minus 3z squared over 3z. All right, so dz dx equals negative 2z squared minus 1 over 3z. Now we can separate them. So that's going to be 3z over. Now those are both negative, so I'm actually going to factor out the negative here, show it up top, so that's 2z squared plus 1. And then just 1 dx. Oh, I forgot the x dx. It's going to go, that's weird. There we go. X dx, integral of both sides. Okay, so you can use substitution. So if you wanted to do u equals 2z squared plus 1, du equals 4z dz. So 1/4 du equals z dz, just with the fractions. So you can factor out the negative 3, and then that's going to be over 4, and that's du over u. That's going to be, oh, what am I doing here? X. A couple mistakes. Okay, This is 1 over x dx. Okay, there we go. Ln of x plus u, plus c. And so this is going to be negative 3/4 ln of u, which is 2z squared plus 1. Okay, so negative 3/4, that's a fourth root. Let's multiply through by negative 4/3. So that's going to be ln, and this is always going to be positive, right, yeah. All right, so now we can bring this to the left. It's going to be a product, so we're going to add, it's going to be adding, so it will be a product of the arguments. 4/3, that will be x to the 4/3. Okay, remember that you're going to have to solve for y squared. So maybe I'm going to just get this out of the logarithm right now. Through by x squared, both sides. Okay, and so that's going to distribute into here. So then you would have 2y squared plus x squared, x to the 4/3, equals e to the negative 4/3 c. Now, this is really a constant, right? So if you want to let, and nothing else is going to affect it. So if you want to let k be e to the negative 4/3 c, then it will just make your solution a little bit easier. So 2y squared plus x squared equals kx squared divided by x to the 4/3. And 2y squared equals, so what's that going to be? That's going to be k to the 6 minus 4 is x to the 2/3 minus x squared. And y squared equals that divided by 2, and then y equals plus or minus that. So it gets pretty complicated. All right. But if you substitute in for that e, that constant, makes it a little bit easier. There's different steps, you know that when you're rearranging, but you do have to get it back down to y equals. Okay, we're just going to look at what the effect of enlarging a graph will do to the equation. So to enlarge a graph by a factor of k means to both horizontally and vertically stretch it about the origin by a factor of k. So enlarge that graph. Think back to transformations from Math 30. So if you're stretching by a factor of k, you're going to replace x with x over k and y with y over k. So that's going to be 2xy over k squared equals x squared over k squared plus 1. Okay, and then it says solve for 2xy. So 2xy equals, that's going to be x squared plus k squared. All right, so really all that's changed there is that that 1 in the original is now k squared. Okay, so if you're stretching both horizontally and vertically. Then it says use implicit differentiation to find dy dx for both equations. So you should know that it's the same because it's a constant, but just quickly do this first one here. So 2x dy dx plus 2y equals 2x plus 0. And then if you solve for dy dx, so the 2's divide out, so you get x dy dx plus y equals x, dy dx equals x minus y over x. This one here, you're going to have the same left side and the same right side because the derivative of k squared is 0, right? All right, is this particular equation a differential equation? Well, a homogeneous differential. So we can show this, remember, as 1 minus y over x. I think that was one of the first examples. So yes, it's a function of y over x. So following statement, if S is a solution curve of a homogeneous differential equation, then any curve obtained from S by enlargement about the origin is also a solution curve. So from example 1a, not this one, the first one, so back to question 1 here, we showed it like this. You could show this as a half factored out. Okay. That was that particular k. Not the same as this particular k. So here, we know that this and this are solution curves for the differential equation. Find the enlargement factor, which transforms this one to this one. Okay, so we are going to replace y with y over k, x with x over k. So here, y with y over k, x with x over k, and then multiply through by k. So you get, if you do, so k over 2, x over k plus k over x. We want to try to make it look like this one. So let's multiply in by k each term, leave the half out. So the k is going to divide out in the first, so you'll just get x, plus then you'll get k squared over x. And now it has to equal 3, so therefore k squared equals 3, k equals plus or minus root 3. And for stretching, we don't incorporate, so that's inadmissible. So k equals the root of 3. Okay, so square root of k. And that's it.